All right. Well, thank you very much for that introduction, and thank you all for coming, and thank you to the organizers for the chance to speak here. So indeed I will be talking about quadratic twists of elliptic curves with free torsion. So for those of you who are at my talk on Thursday, despite the fact that on the schedule these talks have the same title, the content is completely different. Okay. But OK, so this is some recent work that I've been doing jointly with Manjul Bhargava, Zev Klagsbrun, and Ari Schnidman. And it's sort of broadly concerned with ranks of elliptic curves and sort of how they behave in quadratic twist families in certain sort of special cases. Okay? And sort of, I definitely want to talk to you about that and sort of get into some of the guts of it. They're going to be hiding a lot of the technical details ultimately, because this is an intro workshop on analytic number theory. And at the end of the day, what we're going to be doing is we're going to be looking at some sort of Selmer groups and understanding how these things vary via some sort of geometry of numbers argument. And that's sort of, I think, not really sort of the right tone for this audience. So just to start off at a very basic level, this talk is going to be concerned with elliptic curves, given sort of in this short Weierstrass form. But very often I'll be sort of writing down elliptic curves in a slightly different form that's sort of slightly better, or sort of more pleasing to look at the very least. Okay. And sort of the main thing to know here is the Mordell-Weil theorem, which asserts that the rational points on this elliptic curve have the structure of a finitely generated abelian group. Okay. So in particular, if you look at these points, you get some free part and some torsion part. So this number R of E is the rank of an elliptic curve. And this torsion part is of some finite group. And as is common sort of when one puts up a slide of this type, one immediately follows the Mordell-Weil theorem with the theorem of Mazur by saying that the torsion subgroup has been completely classified. It's either sort of cyclic of order n for one of these n's, or it's z mod 2 cross z mod 2n for n up to 4. And so in some sense, kind of all of the interesting action in studying the Mordell-Weil group of elliptic curves is happening with the rank. We still care about torsion. I think it's still interesting which elliptic curves have torsion, and we'll be exploring that a little bit later on. But for the most part, the question is, how does the rank behave? Okay. So just as some kind of very explicit examples, if I look at this elliptic curve, y squared equals x cubed minus x, this is the congruent number elliptic curve. I'll be saying some more things about this in a little bit later. Okay. Then, well, you look at this equation, you see that there are some points on this. You can take x to be 0. You can take x to be plus or minus 1. Okay. And in fact, those are the only rational points. But you also have the point at infinity. Okay. And in particular, this elliptic curve, turns out its group is isomorphic to z mod 2 cross z mod 2. You could also look at, and in particular also, the rank is 0. You could also look at sort of a slightly tweaked version of this equation to sort of make this y squared plus y equals x cubed minus x. Once again, pretty easy to spot at least one rational point on this thing. The point 0, 0 is certainly on here. But it actually turns out that sort of by adding this little bit of plus y here, suddenly 0, 0 is no longer torsion. Okay? And in fact, this thing generates then an infinite subgroup, a cyclic subgroup of this thing. And in fact, it's actually equal to the full group of rational points. Okay? So here's an example where the rank is equal to 1. Okay? And the questions then I'm sort of interested in, well, given any elliptic curve, computing its rank can be hard. Okay? But on the other hand, if you sort of give me some fixed elliptic curve, often it's going to be small enough that I can sort of plug it into Sage or Magma or something like that and just get its rank to pop out. Okay? So for the most part, I'm sort of less interested in sort of the individual ranks of a specific elliptic curve, okay? Especially since, sort of as an analytic number theorist, I'm comfortable assuming big deal conjectures. Okay? And assuming BSD and GRH, there's some algorithm to compute the rank of an elliptic curve. Okay? So the problem of, given an elliptic curve, determine the rank is less interesting to me than the question of how does the rank behave typically. Okay? And so the kinds of questions I'm interested in are then sort of the flavor, well, what is the probability that the rank is equal to m for some integer m? Okay? Or maybe sort of what is the average of this rank? Okay? So here, of course, I should sort of fix some ordering of the elliptic curves to make sense of these probabilities or these averages. If you want, you can sort of assume I'm talking about height here. Sort of the only sort of method of ordering in which we can actually count. But sort of this should be true or interesting questions for any reasonable ordering of elliptic curves. So our motivating philosophy here goes back to work of Goldfeld and Katz and Sarnak. And it's based on the parity phenomenon. So given an elliptic curve, you can write down its L function. And just like the Riemann zeta function, it satisfies a symmetry, sending s to 2 minus s in this case. Okay. And it turns out, though, that this comes equipped with a sign. Okay. So it comes equipped with this number w of e, which is plus or minus 1. And this root number, okay, dictates a lot about the structure of this elliptic curve. Okay. So BSD, okay, simply asserts that the rank of the elliptic curve is equal to the order of vanishing of this L function at the central point, s equals 1. Okay. So if you understand the root number, you understand the parity of the right-hand side, and so you expect you understand the parity of the left-hand side. And that's exactly what the parity conjecture asserts. Okay. So if you were at Chantal David's talk last Friday, this sort of played sort of a key role kind of in motivating her work on the distribution of the root number in various families. Okay. All right. Well, what is this number w of e? Okay. Well, it takes values either 1 or negative 1. Okay. It seems pretty reasonable to guess then that probably it should be sort of evenly distributed between these two possibilities. Okay. Absent outside information, you may as well guess that the root number is going to be plus 1 50% of the time and minus 1 50% of the time. Okay. And also sort of believing that it's hard for there to be more rational points than you sort of have a good reason to expect. Okay. So sort of the so-called minimality hypothesis. Sort of led Katz and Sarnak to conjecture that 50% of elliptic curves have rank 0 and 50% have rank 1. Okay. And there's been some remarkable recent progress toward sort of this conjecture. And it's now, I guess, a couple of years old, but I still think it is sort of mind-blowingly sort of beautiful and kind of incredible that we can prove these things. Okay. And in particular, using work of Bhargava and Shankar and Bhargava, Skinner, and Zhang, okay, you can prove that at least 20% of elliptic curves have rank 0, and at least 20% have rank 1. Okay. All right. And so I should say, well, this conjecture is indeed a conjecture. It is open. Okay. And you could ask, how does this sort of phenomenon behave or change if you restrict to certain subfamilies? Okay. And in particular, a very natural family to look at is the family of quadratic twists. So let E be an elliptic curve. Okay. And we're going to take this elliptic curve and we're going to start changing it very slightly. Okay. And in particular, all we're going to do is I'm going to throw in a d on the left-hand side. Okay. So I'm going to modify the equation in this form. Okay. It's going to be dy squared equals x cubed plus ax plus b. If you're really sort of wedded to the short Weierstrass model, you can sort of write it like this as well. But I think this is a little bit more natural to look at. Okay. And the reason why this is sort of an interesting thing to do, okay, or why we call it a quadratic twist, is if you pretend that we're allowed to take square roots of d. Okay, then I could take this d inside sort of this y squared, okay, and I'd obtain an isomorphic elliptic curve. Okay. So if I'm allowed to talk about the square root of d, I have an isomorphic elliptic curve. I haven't done anything. Okay. But if I'm not allowed to talk about the square root of d, meaning, say, d is square free, okay, then I get a different elliptic curve which is isomorphic over some extension of Q. Okay. So this is sort of where this terminology quadratic twist comes from. Okay. And the point is this is some nice family. Okay. And in particular, in the context of root numbers, okay, we know, actually, that root numbers are equidistributed. 50% of root numbers are plus 1, and 50% are minus 1. And so because of this, Goldfeld conjectured sort of the analog of Katz-Sarnak, although sort of saying that is kind of backwards. Okay? Because in fact, Goldfeld's conjecture predates the conjecture of Katz and Sarnak, and arguably sort of motivation for the conjecture of Katz and Sarnak as well. Okay. So we have Goldfeld's conjecture. You feel like we know more about root numbers in this family of quadratic twists, okay, than we do in the full family. I've sort of been talking to you about root numbers as sort of like the reason why, how you should think about these things. And yet, embarrassingly, we don't have sort of the analog of this Bhargava-Shankar, Bhargava-Skinner-Zhang result, okay, and it's sort of in full generality. Okay. So in particular, the question sort of that's motivating this talk, okay, is what you might call weak Goldfeld. Okay. This is sometimes attached to analytic ranks. Here I'm really talking about algebraic rank. Okay. And the question is just, do you get rank 0 and rank 1 a positive proportion of the time? Okay. So I think the first real breakthrough result, sort of along these lines, goes back to Heath-Brown. Okay. So let E be this elliptic curve, the congruent number elliptic curve. Okay. That was sort of the first elliptic curve whose Mordell-Weil group we looked at. Okay. And in particular, this Mordell-Weil group was Z2 cross Z2. Okay. It is sort of the full two torsion, and that's it. Okay. And what Heath-Brown proves, okay, he does more than what I'm about to say. Okay. But a consequence of his work is that the average rank of this elliptic curve, okay, as you vary in the quadratic twist family, is bounded by 3/2. Okay. You can show that the rank is 0 for at least 20.9% of D. This value 20.9 comes about as the value of some infinite product, okay, but it's completely explicit. Okay. And you can also prove that the rank is 1 for a pretty large proportion of twists, okay, if you're willing to assume the finiteness of Shaw. Okay.
Everything is under GRH unless you're talking about analytic rank, right?
No, I'm talking about arithmetic rank here. Okay, I do not need GRH. He did not assume GRH. You do not need GRH for this.
Yeah, because he bounded the analytic rank. Otherwise,
this is a different paper. So this is a paper where he looks at the computation of the two Selmer groups. He looks at the two Selmer groups, and you prove that this proportion of two Selmer groups have two Selmer rank 2, which matches the two torsion rank, so the rank of the elliptic curve is forced to be 0. Okay. Yeah, so it's a different argument. He also has a paper where he looks at, yeah, this is a good point, where he sort of looks at analytic ranks sort of by something like sort of a one-level density, for example, of a family of elliptic curves or something like that. I can't remember exactly the argument. But yeah, that's a different paper. This one is about two Selmer ranks. Okay. Yeah, well, I mean, yeah. OK. But yes, this is unconditional. This is arithmetic. This does not belong in an analytic number theory talk or session, and yet here we are. All right. OK. So I'll say a little bit about this finiteness of Shaw condition in a second. Okay. But it's also worth pointing out that in recent work of Alexander Smith, you can actually show that you get rank 1 for a positive portion of D unconditionally, without this sort of assumption of finiteness of Shaw. Okay? And this is a different style of argument. Okay, you need to sort of control the analytic rank here. Okay? And so he does this by sort of looking at kind of the two parts of these L values and actually sort of coming up with an actual expression for these things and sort of controlling it that way. Okay? All right. But Heath-Brown's result is sort of what I mostly want to focus on. Okay? And to tell you kind of loosely how it goes, okay, we're going to use two Selmer groups, okay, as I sort of have been saying. Okay? And what a two Selmer group is, I'm not going to give you the exact definition. Okay? The exact definition, I think, doesn't really belong in this talk. It won't be particularly illuminating if you haven't seen it before. But the important thing to know is that sort of the Mordell-Weil group sits inside the two Selmer group. Okay? So in particular, if you look at E mod 2E, this embeds into the two Selmer group. Okay? And you want to think about this as saying, well, we want to understand the Mordell-Weil group. Okay? The Mordell-Weil group is something that's sort of very hard to get our hands on explicitly. We want some way of putting it into something which we do understand. Okay? And that's sort of what this two Selmer group is supposed to do. Okay? So in particular, the way one usually proves the Mordell-Weil theorem is one first proves what's called the weak Mordell-Weil theorem. And that essentially amounts to proving that, say, the two Selmer group is a finite group. Okay? But of course, if you have something which is hard to understand embedded into something which is in principle easy to understand, okay, you should imagine that the quotient is going to be hard to understand. Okay? And so this is the Tate-Schaffer-Raevich group, and particularly we see the two torsion part of it in this exact sequence. Okay? All right. And so kind of the key thing I want you to take away from this, okay, is that the two Selmer group kind of behaves like an algebraic proxy, okay, for the Mordell-Weil group. Okay? If you want sort of some kind of very loose sort of moral description of what this two Selmer group is, it's kind of the points that sort of locally everywhere look like they should be on sort of E mod 2E. Okay? You can make that precise. Okay? Well, that's kind of the loose idea. Okay? And in particular, well, this two Selmer group is some abelian 2 group. Its order is 2 to some number. Okay? And this thing has to be an upper bound for the size of sort of this group, E mod 2E. Okay? And in particular, it turns out that that group is of size 2 to the rank plus 2, okay? Where this plus 2 comes about from the two torsion subgroup of the elliptic curve. Okay? All right. And so the idea that sort of underlies Heath-Brown's work is to study the distribution of this two Selmer rank, okay? Sort of the order of the two Selmer group. Okay? And in particular, what he does is he nails down, he shows that, in fact, sort of these two Selmer ranks obey a limiting probability distribution, that there is some sort of limiting probability that this two Selmer rank is 0. That's exactly what gives you this 20.9%. Okay? he shows that there's some limiting probability that the two-Selmer rank is 1, which is exactly what gives you sort of the 41.9%, okay, from that previous slide. And so kind of what I should say here, I needed to bump those numbers up by 2. Okay. For example, suppose you can show that the two-Selmer rank is equal to 2. Okay. Then this sort of doesn't give you any room to have rank. Okay. And so in particular, if you show that sort of two-Selmer rank 2 happens with positive probability, then you've automatically shown that rank 0 happens with positive probability. Okay. To get from two-Selmer rank 1, or 3, to rank 1, okay, it requires more work, because this inequality just tells you that the rank is bounded by 1. Okay? And so this is where this assumption on the finiteness of SHA comes into play. If SHA is finite, then we know its order is a square. Okay? And you have some sort of parity condition popping up here that forces, in this case, the rank to be exactly equal to 1. Okay? But OK. So I'm actually going to go a little bit farther into the guts of Heath-Brown's proof, okay, to sort of give you some idea of what's going on here. And this might sound a little bit scary. I mean, we're talking about Selmer groups whose definitions I haven't given to you and kind of don't want to give to you. But it actually turns out in this case that these two Selmer groups are very natural things. And it turns out in particular that their elements, okay, correspond to certain kinds of biquadratic extensions of Q. Okay. So if you were at Jordan Ellenberg's talk yesterday, okay, he sort of gave biquadratic fields as almost like the second simplest example of fields which we can count. Okay? If we sort of just count quadratic fields, well, that's just counting square-free integers. Okay? To count biquadratic fields, well, you're just counting pairs of square-free integers. Yeah, you did. Thank you. Yeah. I mean, I'll admit I wrote my slides after your talk, but anyway. But yeah, and so you sort of end up in particular. So he had this question, why not, okay, about sort of why you might see a log showing up sort of in the count of biquadratic fields. And this is exactly corresponding to summing up the divisor function. The discriminant of this thing is essentially m1 squared, m2 squared. Okay? All right, so we know how to count biquadratic fields very well. Okay? Well, it's not just sort of all biquadratic fields we need to be looking at. Okay? The elements of this two-Selmer group correspond to biquadratic fields that are unramified away from 2D, okay? Meaning that the primes that show up sort of in m1 and m2 are very limited. They have to divide 2D, and maybe you can throw in a -1 as well. Okay? So that already sort of says that this two-Selmer group is going to be finite. It gives you a very explicit sort of upper bound on this thing. Okay? And in fact, well, it's not this two-Selmer group is all of those things. Okay? There are a whole bunch of local conditions that need to be satisfied as well. Okay? And these local conditions are a pain. Okay? These local conditions depend on each other. Okay? So it's not just like you're saying, well, let's ensure that our field is sort of, say, split completely at such and such primes, or something like that. These local conditions really depend on each other. Okay? And so it's kind of a big analytic mess to disentangle these conditions, okay? But this is something that we are able to do. Okay. Okay. So kind of secretly, okay, what's going on in this sort of perspective, okay, which I don't really want to say very much about, okay, is that the two-Selmer group sits inside some Galois cohomology group. So again, to sort of use Jordan's talk, Jordan put up some cohomology group of some legitimate topological space. Here is some Galois cohomology group. Okay? This should be probably even more frightening. Okay? But one of the things I want you to take away from this talk, if you really don't like Galois cohomology, okay, is you can be slightly less afraid of these things. Okay? Okay? Because in particular, it turns out, okay, that this two-torsion subgroup of the elliptic curve, okay, well, we know what that is. Okay? We know that these elliptic curves have full two-torsion. It's Z2 cross Z2. And in fact, the two-torsion, sort of its Galois structure doesn't change as you vary in quadratic twist families. Okay? And so you actually have that this two-Selmer group sits inside this sort of fixed H1Q, Z2 cross Z2. Okay? And it turns out that this actually corresponds pretty much exactly to this set of biquadratic fields, because biquadratic fields are the things which have Galois group Z2 cross Z2. Okay? So you can sort of see something like this. This basically means you're counting biquadratic fields. So it's sort of not quite as scary as it might otherwise be. Okay. But yeah, let's mostly ignore this picture. OK. So okay, what makes this argument work? Okay. Well, there's definitely some hard work to be done kind of at this third bullet. Okay. But the key ingredients really are just that this elliptic curve has full two-torsion. Okay. And in particular, it's a theorem of Dan Kane, building on work of Swinnerton Dyer, that if you have an elliptic curve with full two-torsion, then you can get the exact analog of Heath-Brown's result. Okay. All right. So we're in a very good situation towards a sort of weak Goldfeld conjecture if you have an elliptic curve with full 2 torsion. But that feels like a pretty special condition. Okay. And you can ask, how common are these elliptic curves with full 2 torsion? Okay. Well, now I need to say a little bit about how I'm ordering elliptic curves. Okay. We're doing so by height. Okay. So given an elliptic curve in short Weierstrass form with integral coefficients, okay, let the naive height sort of be the max of a cubed and b squared. Okay. And, well, it's a pretty basic fact that there are 4 over zeta 10 times x to the 5 6 elliptic curves, or non-isomorphic elliptic curves, of height up to x. Okay. So the x to the 5 6 is coming about from 1/3 plus 1/2. Okay. The 4 is because we're allowing plus or minus in each of these variables. Okay. And this zeta 10 is coming about from this non-isomorphic condition. Okay. So there's some scaling you can do on your coefficients here. Okay. You can scale a by a factor of p to the 4th, b by a factor of p to the 6th, and get the same elliptic curve. So you should basically think of this sort of 1 over zeta 10 as being analogous to the 1 over zeta 2 you see when counting pairs of relatively prime integers. Okay. So this is actually very easy to prove once you sort of have the right notions in mind. Okay. And it turns out, well, if you want to count elliptic curves with a given torsion subgroup, you can do this. Okay. And it's a theorem of Heron and Snowden, sort of that in this particular case, you get x to the 1/3 non-isomorphic elliptic curves with height up to x and this full 2 torsion. So I actually really like this paper of Heron and Snowden. Okay? It appeared a couple years ago in Krella. Okay? And again, they do sort of pretty much what I said. They sort of look at how often do you get sort of each of these torsion groups that appear over Q. Okay? And they sort of obtain analogous results sort of for everything of that type. Okay? So in particular, we sort of have a quantified version of saying that having this 2 torsion group is very rare. Okay? You see only x to the 1/3 out of x to the 5 6. And so you might ask, are there bigger families for which we can prove weak Goldfeld? Okay. I must have lied. Yes. This is also surely a true statement, but yeah, they prove 2 torsion part. Okay. Okay. Yeah, very good point. Okay. You sort of look at the 2 torsion subgroup of the elliptic curve, and you get z2 cross z2. So what goes into their proof is you can actually write down a universal elliptic curve for elliptic curves with full 2 torsion. Okay. And then so you just sort of kind of get some basic sort of arguments saying, OK, well, the variables sort of have to range in this sort of in this region. And then it actually gets pretty hairy. I mean, you sort of have this sort of minimality conditions that I'm sort of hiding in here, sort of that lead to this zeta 10, that actually become much trickier sort of for these universal curves that sort of, and also sort of the geometry gets a little bit ugly, and you sort of get this asymptotic sort of rather than sort of the full sort of asymptotic, if that makes sense. Okay. But yeah, so it's a very nice paper. They were sort of able to get asymptotics in some new cases, in particular for, say, 3 torsion. They get an actual asymptotic. But anyway. OK. So the question is, again, are there some bigger families for which we can prove a result of this type? Okay. And that is the structure of our work. So let E be an elliptic curve with a 3 isogeny, okay, which, if you're not familiar with the terminology, I'll make precise in a second. Okay. Then what we're able to prove is essentially an analog of Heath-Brown's result. Okay. Then you can show that the average rank of the quadratic twist family is bounded, okay, that a positive proportion of twists have rank 0, okay, and a positive proportion of twists have rank 1, assuming finiteness of Shaw. Okay. And so a couple of remarks are in order. The first is that kind of by completely different methods, Kriz and Lee recently, I think paper went up maybe in November on the archive, that you can actually get a positive proportion of twists with rank 0 and rank 1 unconditionally. Okay? But they do not get a result on the average rank, and their proportions are actually also much weaker. Okay? Without assuming finiteness of Shaw. Yeah. So they look at analytic methods and they basically prove that a positive proportion of these things have L value that sort of vanishes to single order and sort of then has the right properties with respect to BSD. Okay. Yeah, so this is using some converse theorems to Gross-Zagier. So it's actually sort of very deep work. but it's of a different flavor than what we do. And again, it sort of forces you to have more restrictions on the twists you look at, and kind of analogous to how Smith had a lower proportion than Heath-Brown did for the rank 1 twists. We can sort of do kind of much better for generic elliptic curves. They're not fixing attention on elliptic curves with J invariant 0. Okay. They have this in sort of the same level of generality that we do. Okay. And the second remark is just sort of justifying my motivation for looking at this family, that I wanted something slightly bigger than Heath-Brown's family. Okay. Well, it turns out that you get basically x to 1/2 elliptic curves with a 3 isogeny. Okay. Okay. All right. So I should also say that all of these results are completely explicit. Okay. And I think it's actually worth seeing a very explicit example of this. Okay. So let E be this elliptic curve. Okay. It turns out that this thing has a 3 isogeny. Okay. And our results take the following shape. Okay. The average rank of the twists is at most 7/6. Okay. We can show that the elliptic twist is rank 0 for 25% of twists D. Okay, and this is also an honest-to-God 25%, not some horrible infinite product I've rounded. Okay, this is 1/2 times 1/2. Okay, and we can show that sort of the rank is 1 for at least 5/12 of twists, assuming finiteness of Shaw. Okay. So I'm about to give you an equivalent condition, but basically the idea is that you have a 3 isogeny if and only if a quadratic twist has a 3 torsion point. Okay. All right. Okay. And I should say that exactly the same corollary holds for some other elliptic curves as well, but sort of these numbers are going to change sort of in general. Okay. We give you some explicit recipe to compute these things, but for these elliptic curves, for example, it is sort of as nice as it can get. Okay. All right. So what is this isogeny condition? Okay. Well, an M isogeny is a degree M rational function from one elliptic curve to another, okay, that also respects the group law. Okay. And so you can kind of imagine that maybe by mucking around with equations, it's sort of you can come up with some rational function that takes points on this elliptic curve to points on that elliptic curve. Okay. But it should probably be pretty hard to make it also simultaneously respect the group law and be a homomorphism. Okay. And an example, though, to prove that isogenies do indeed exist, is that multiplication by m works as an isogeny. Okay? And it's an isogeny of degree m squared. Okay. All right. Okay. And this is the fact that sort of I just brought up in response to Chantal's question. But you have a nice characterization of what it means to have a 3 isogeny. Okay? You have a 3 isogeny if and only if some quadratic twist has a 3 torsion point. Okay. All right. Okay. What is? Not over Q. Not over Q. You cannot have full 3 torsion over Q because you do not have, yeah, you sort of need third roots of unity to get full 3 torsion. And so you don't have that over Q. Okay. But yeah. Okay. In general, you're right that I should just sort of say, sort of, if I change what Q is, then yeah, I need to say it just has a 3 torsion point rather than 3 torsion subgroup isomorphic to blah. Okay. What I mean by degree is essentially number of preimages over C. Okay. Okay. Yeah. So I can make this explicit. Okay. So returning to the elliptic curve that we said just gave in this corollary, okay, well, it turns out that this Mordell-Weil group, okay, is isomorphic to Z mod 3 generated by the point 0, 0. Okay. And so by this sort of lemma, we know that this thing is going to have a 3 isogeny because some quadratic twist has a 3 torsion point, in particular the trivial twist. Okay. If you let this elliptic curve be as here, then this rational function exists. Okay. Here it is. Okay. And I don't bring this up to say, oh, here, this sort of rational function is particularly illuminating. I just sort of want to point out that you can do this at a very explicit level. Okay. You can kind of see that the degree is going to be 3 just sort of by saying, well, suppose this equals your favorite number. You can just solve this equation. You see that the degree is 3. Okay. And you should imagine also that this is sort of kind of interesting. Okay. You sort of take rational points on your elliptic curve, E, you go to E prime. Okay. this sort of ties the structure together, okay, in a certain way. Okay? And so in particular, if you have an isogeny between two elliptic curves, then they have to have the same rank. Okay? So for example, this elliptic curve has rank 0, so this one also has rank 0. Okay? As soon as you get an interesting point, so maybe you say work over q join square root of 2. Okay? It turns out then you have rank 1 here. Then just moving that rational point forward under this isogeny gives you a point on E prime. And so two elliptic curves, if they're isogynous, they must have the same rank. And in fact, they have to have a lot of the same structure in common. And the point of what we do is we're going to use the Phi-Selmer group to access the rank. All right. So again, I'm not really wanting to define what the Phi-Selmer group is. But it turns out it sits in kind of an analogous exact sequence as we saw with the 2-Selmer group. So we have, again, sort of this Mordell-Weil group, okay, or sort of slightly tweaked, okay, that we want to understand, embedded into something that I am telling you we can explicitly understand, okay, in some sense. Okay. And, well, then, as before, you get some quotient that is some torsion in a Tate-Schaffer-Abich group. Okay. Okay. And really what we prove is this. Okay. Suppose you have an elliptic curve with a 3 isogeny. Okay. Then we give you some exact expression for the average size of this isogeny-Selmer group. Okay. So I have not told you what the isogeny-Selmer group is. I haven't really motivated what this right-hand side is either. Okay. Here it is. It's given by some formula. Okay. I mean, it's actually a pretty nice formula once you parse what it says, but what I want you to take is that this is something very explicit. Okay. Okay. It's going to depend basically on the primes of bad reduction, okay, of something which you can compute. And in particular, this is some rational number. Okay. This is something we can just work out explicitly. Okay. All right.
Just for clarification, what does ED prime stands for?
ED prime, so is the quadratic twist of E prime by the same D you're twisting E by. Okay. So it actually turns out that if you have an isogeny between two elliptic curves, you can actually twist that isogeny. Okay. And so this is basically just saying then, you're just keeping track of that. Okay? And sort of always have, sort of in the quadratic twist family, you have one elliptic curve pinned against sort of the other isogynous elliptic curve. And we're sort of understanding is how do these different Selmer groups sort of play against each other.
But so let me understand, I mean, because that thing you're averaging inside,
Yes.
has to do with the p-adic geometry of the elliptic curve. Now that you're saying that,
Yes.
that in principle, if I hand you an equation,
Yes.
you can just sit down for a minute and then like write down a real number. Is that
That is exactly right.
okay? So there's no mystery left inside that.
That is exactly right. Yes, yes, that is a very good point from Jordan. Thank you. Yeah, so this thing here is just going to depend basically on how D behaves in QP cross mod QP cross squared. Okay? It's just going to depend on sort of the structure of sort of the quadratic extension of QP given by D. Okay? And so it's something you can compute very explicitly. This is some just rational number you can write down. Yes?
Is there a reason for the naming
This is indeed sort of the Tamagawa number. Okay. Yeah. All right. So what I'm going to do is I'm going to make things look a little bit worse for you, but it's also going to clean things up a bit. Okay. So what I want to do is I want to say let sort of the global, what we call a global Selmer ratio, okay, be given by the product of these Tamagawa numbers, be the product of these things here. Okay. Okay. Then it turns out, okay, this thing is always a power of 3. Okay. And what we want to do is we want to sort our twists D by the power of 3 we get. Okay. Okay. Then what we really prove is the following. Okay. That this set is empty, okay, for all but finitely many integers m. Okay. That each non-empty Tm is positive density. Okay. And in fact, it's actually something very explicit. Okay. Each of these Tm's is going to be cut out by finitely many sign conditions and congruence conditions. Okay. I'll give you an example of this on the next slide, okay, to try to sort of demystify things a lot. Okay. Okay. If you twist inside sort of Tm, okay, then it turns out that the average size of this Phi-Selmer group is exactly 1 plus 3 to the m. Okay. Okay. It turns out that the sort of average rank, okay, is at most absolute value of m plus 3 to the minus absolute value of m. Okay. This thing could be a negative power of 3. The proportion of twists that we get that have rank 0 is, in fact, actually just given by this t0. We get 50% of the twists in t0 have rank 0. Okay. And something similar holds for our twists with rank 1. Okay. All right. Let's try to demystify this. Let's return to our example. Did you want that slide up for a little bit longer?
I just think it's funny that you express things in terms of the average rank when you're showing that. I mean, you're showing that something that's much bigger, like something that's like the rank, has an average. That's much more impressive somehow. I mean, I feel like it's. Right. I mean, the fact that the size of the Selmer group has an average, like.
So yeah, I actually find this sort of to be kind of a very appealing fact. Yes, and it's sort of actually kind of exactly corresponding to what you'd expect sort of from sort of fixing this sort of global Selmer ratio. This is sort of exactly fixing kind of this average that we were taking. We're restricting to twists where we know exactly what this average is. Okay? And we're sort of basically proving is that in this case. Okay? But sort of as far as like averaging sort of this 1 plus 3 to the m and being surprised that this 3 to the m gives us something finite, well, Tm is empty for all but finitely many integers m. Okay? Mm-hmm.
I know, but I think it would be a great paper if they never mentioned Mordell rank. That's all I'm saying.
Yeah.
I mean, it's not really your paper is not really about Mordell rank.
That's right. Yeah, that is exactly right. I mean, it has some nice consequences for Mordell rank, but yeah, no, it is really sort of about understanding these Phi-Selmer groups. Okay? That's exactly right. Okay. So again, let's try to demystify this and sort of see how things actually work in practice, and to convince you that maybe you sort of don't like everything I've been saying. You're really unhappy with Phi-Selmer groups. You're really unhappy with all of these, Tamagawa numbers and sort of everything like that. Okay? I want to convince you that this is something that can actually be understood pretty easily, okay? Even in an intro analytic number theory workshop. Okay? Well, it turns out so that this elliptic curve that I wrote down here has conductor 19. Okay? So that means that the only prime of bad reduction is 19. And well, you also have to worry about infinity. Okay? This is basically corresponding to are you twisting by something that's positive or negative. Okay? And well, this factor here just kind of exactly corresponds to that. Okay? If you're twisting by something positive, you get 1. If you're twisting by something negative, you get 1/3. Okay? How does this C19 in phi d behave? Okay? Well, it's given by something like this. Okay? It's either 3 or 1, okay, according to these two conditions. So in particular, the probability that it's 3 is just slightly less than 1/2. Okay. All right. And so then the kind of things we do sort of to prove, say, this corollary that I presented, okay, is we just say, well, we want to understand sort of the various possibilities of getting these TMs. Okay. So here in particular, we know that if you multiply these two things together, well, you're going to get something between 1/3, 1, and 3. So we know that it's supported on M in this set. Okay. Moreover, let's say you want to get rank 0, Tm being 0. Okay. Well, then either you're combining the two 1s or you're combining the two 3s. You understand all of these probabilities. Okay. You can just work this out very easily. Okay. And in fact, it turns out sort of say the density of this set T0 within the set of square free integers is 1/2. Okay. And from that, okay, you can get, for example, that the rank is 0 for half of that density, so 1/4 of twist d. Okay. And so this is something that can be made completely explicit. You can code this up in Sage, okay, and completely forget about having to do any hard computations by yourself. Okay. All right. So where does this come from? Okay. Well, it turns out if you have an elliptic curve with a 3 isogeny, you can write it in this form. Okay. This is sort of an example of kind of the universal elliptic curves, for example, that showed up in the work of Herod and Snowden, sort of uncounting elliptic curves sort of when ordered by height with specified torsion subgroup. Okay. So you write down some universal elliptic curve. It turns out this is a good choice for one. Okay. Okay. And very loosely, okay, elements of this Phi-Selmer group are now going to correspond to cubic fields. Okay. So when we're looking at the 2-Selmer group in families of quadratic twists, okay, we saw that sort of these 2-Selmer elements corresponded to these biquadratic fields. Okay. Kind of the second easiest kinds of fields to count. Okay. these elements correspond to cubic fields. And essentially the reason for this is that sort of the kernel of this isogeny, the fact that it's degree 3, sort of suggests this cubic. We understand sort of more restrictions on these things. They have to be unramified away from primes dividing 6 times twisting factor times this d. OK? And which satisfy some local conditions at the various primes dividing sort of this number. And so when we do things like, say, restricted twists inside some TM, what we're really doing is kind of fixing these local conditions in a certain sense, okay, making it very easy to understand how these things behave. Okay. I'm lying kind of slightly here. Really, what I should be saying is that elements of Heath-Selmer correspond to binary cubic forms. Okay. So the way you sort of see a connection between binary cubic forms and cubic fields goes back to the work of Dolina and Fadeev, who proved that cubic fields correspond to GL2Z equivalence classes of binary cubic forms. Okay. But not all binary cubic forms sort of arise in this way. You need to restrict to those that are irreducible and maximal. Okay. So these conditions, roughly speaking, translate to saying, well, irreducible means you're actually getting cubic fields. Maximal is some condition that ensures you're counting the maximal order in a cubic field. Or equivalent is just sort of saying, I'm counting each cubic field exactly once. Okay. So this is a beautiful theorem. And there's sort of quite a bit more that's sort of true here. I mean, this is a discriminant preserving correspondence. Okay. But it was used beautifully by Davenport and Heilbronn to count the number of cubic fields of discriminant up to x. Okay. And in particular, it turns out to be asymptotic to 1 over 3 zeta of 3 times x. Okay. And the idea of the proof here is, well, just use Dolina-Fadeev and geometry of numbers. Okay. So I'm sweeping a tremendous amount under the rug when I say that. But that's sort of roughly the sort of sketch of the A proof. You have cubic fields being parameterized by something interesting, which you can just sort of write down very explicitly. This is some 4-dimensional vector space with a group action. You write down some fundamental domain. You try to count lattice points. Okay. So our idea is to do something like this for Heath-Selmer. Okay. And indeed, kind of the crux of our paper is proving a parameterization of what these Heath-Selmer elements correspond to. And in particular, it turns out it takes the following shape. Okay. So this is really kind of the key step in our paper, okay, is that you can think of these Heath-Selmer elements, okay, as SL2Q orbits of some integral binary cubic forms satisfying some local conditions, okay, with some specified discriminant. Okay. And so again, this is maybe a mouthful, sort of hard to parse, but the idea here is that we turn these Heath-Selmer elements, which we sort of want to understand explicitly, into something which we can use geometry of numbers ideas to attack. Okay. And in fact, really kind of the key idea of our proof is just use geometry of numbers results. We can actually almost port in directly existing results on the distribution of binary cubic forms and this parameterization to count these Heath-Selmer elements. Yes? I'm going to get to you in a second, Jordan. Joseph. Yeah, what is locally E-soluble? So it turns out that sort of these binary cubic forms has to satisfy some local conditions. Okay? And basically, it's not sort of saying that these things are locally soluble. This is not what it means. Okay? Instead, what it means is that if you look at these things, p-adically, they should be in the image of the Kummer map for every prime p. Okay? And you can sort of parameterize that very explicitly. Okay? You can sort of say, here is exactly what sort of local E-solubility means. Okay? And I should also say that this theorem, this parameterization, is completely explicit. Okay. We say, OK, great, you have this binary cubic form with satisfying our conditions. Here's your Heath-Selmer element. Okay. We can write this down very explicitly. Okay. Okay.
So I'm not sure I understand that. If you and I are each thinking of an elliptic curve with a 3 isogeny,
yes,
the same capital D, but you have one little a and little b, and I have a different one, are you saying that there's an identification between the Heath-Selmer groups of the two? I mean, those elliptic curves have nothing to do with each other, right?
Those elliptic curves have nothing to do with each other. I would suspect that sort of the local solubility conditions will change a little bit there.
Oh, OK.
Okay, so you're sort of actually sort of looking in the same space, but cutting out different forms.
I see. There is some dependence on which of the
There's
curve actually is hiding in there.
absolutely some dependence on the, yeah, exactly. That's sort of, I am putting E there for a reason.
Oh,
Okay.
right. I see it.
M also depends on E. That's sort of just kind of an annoyance that sort of we're looking at. We want to look at orbits sort of with integral points, but up to rational equivalence. We sort of need to kind of rejigger things a little bit to ensure we're sort of getting integral orbits in the first place. But yeah, and it's also worth noting sort of that the Delaunay-Faddeev correspondence sort of says cubic fields correspond to GL2Z orbits. Here we're sort of looking at SL2Q. There's a little bit of sort of work needed to go back and forth between the two, but it turns out you can understand how rational orbits break up into integral orbits, at least for typical elements of these things. Okay. So I don't really want to say too much more about the proof. Okay. I mean, certainly happy to talk to people after the talk about this. But let me just sort of, again, kind of reiterate what we really sort of, this is kind of the heart of what we actually prove. Okay, this is kind of the thing that sort of makes everything get started, is the realization that these Heath-Brown elements correspond to some very explicit conditions of binary cubic forms. Okay. And using it, we sort of prove these various applications to ranks. Okay. And again, so these are completely explicit. For your favorite elliptic curve, you can compute these various densities by doing something very similar to what we did kind of in that example. Okay. But this leaves open a question. It sort of feels a little bit unsatisfying because it doesn't tell you how do these results actually depend on the elliptic curve. Okay. All right. So in particular, we have some understanding of these things. Okay. And well, it's going to be sensitive to the number of bad primes. Sort of as you get more and more bad primes, you have sort of more Tamagawa factors to look at. Okay. You have more things sort of contributing to this product sort of that we just had before, where we had a C infinity and a C19. If you have a lot more of those things to work with, each individual guy is very explicit. Okay, but sort of combining them together, you can do, but it's sort of you have to understand kind of in general. Okay. But what I can say is for typical elliptic curves, you get a bound in the average rank sort of roughly of this shape, okay, square root of log conductor. Okay. Okay. And the proportion of D we get is bounded below by about 1 over square root of log. Okay. And the same holds for rank 1 twists. Okay. This is for typical elliptic curves. Okay. You can also cook up some kind of extreme examples, okay, by saying, OK, I want an elliptic curve which has multiplicative reduction of such and such type at a whole bunch of primes and very little other kind of bad reduction going on. Sort of playing those sorts of games, it's possible to cook up kind of extreme elliptic curves for which the bound in the average rank is something like this, and the proportion you get is something of this type. Okay. And we do also get a lower bound for rank 1 twists here, but again, it's going to be of exactly the same shape. These are all Selmer ranks, but then basically immediately applying this to actual ranks, we get this. Okay. All right. Okay. So this is probably kind of unsatisfying. Okay. I mean, on the one hand, like log goes to infinity really slowly. Okay. So this is not a very big bound. Okay. So for typical elliptic curves, you're going to get a pretty small bound in the average rank. Okay. On the other hand, log does go to infinity. Okay. And so you should be asking, like, are we just sort of being inefficient in what we're doing here? Okay. Or is there something kind of weird happening with Heath-Selmer? Okay. I mean, I hope sort of you believe sort of from the sketch of the proof I gave you that we're probably not being that inefficient. Okay. But maybe sort of you question this result. Or maybe you ask, well, I'm interested in things more than just quadratic twists. Okay. Can you say anything about sort of how all elliptic curves with a 3 isogeny behave? Okay. And that's actually something that in separate work with Zev, we kind of understand. Okay. So going back to kind of the breakthrough work of Bhargava and Shankar, they computed the average size of the M-Selmer group kind of in the family of all elliptic curves. Okay. As you vary over all elliptic curves, the average size of the M-Selmer group is this very pretty sum of divisors of M, okay, when M is no bigger than 5. Okay. Okay. So in particular, most elliptic curves have a bounded number of Selmer elements. Okay. What Zev and I show is, well, let's say P is 3, 5, 7, or 13. Okay. You might recognize those primes, some of you. Okay. And let E range over elliptic curves with a P isogeny, okay, and some notion of height up to x. Okay. Then the average size of the Phi-Selmer group, so we're in kind of the same world we were in sort of on the previous slide, just now varying over all elliptic curves with a 3 isogeny or with a P isogeny. Okay. So if we sort of had some analog of Bhargava and Shankar, we should expect some bounded number, something like sigma of m. Life ain't that pretty. Okay. In fact, sort of the average size of these Selmer groups sort of grow like log x to some power. And in particular, just applying this for p equals 3, we find that the average size of the Phi-Selmer group grows like log x to the 2/3. Okay. And I should say a couple of things on this slide. Okay. First off, we think these are actually the right answers. Okay. We think that sort of there should actually be an asymptotic formula for the average size of the Phi-Selmer group that is some constant times this power of log. Okay. In particular down here as well. Okay. Some other things I should say. This modified notion of height is a pretty reasonable thing to be doing. Okay. So the reason why we have these primes and not, say, 11, okay, is the fact that the modular curve x naught of p has genus 0 for these primes p, and not, say, for 11. Okay. And so what we're really using, sort of turning that into analytic number theory language, okay, there are infinitely many and lots of elliptic curves with these sorts of isogenies. Okay. There are only finitely many elliptic curves with other kinds of isogenies for other primes p. Okay, we sort of want to sort of have this ability to play with things. We want the ability to write down explicit families of elliptic curves. Okay. And our result is also much more general than this. Okay. We can sort of be given sort of any genus 0 modular curve with some notion of what it means to have an isogeny for this elliptic curve on this modular curve. Okay. And we give you some recipe that in terms of the geometric data of that modular curve outputs a lower bound of this type, which we expect to be optimal. Okay. All right.
Robert, is this saying that the conjunction of these two theorems, are you saying that if you look at the ones with a 3 isogeny, those have, I mean, after all, the whole 3-Selmer rank of that has to be at least the 3-Selmer rank.
Mm-hmm.
I sort of feel like what's going on is there's like lots of ambient curves without a 3 isogeny, which have like very low 3-Selmer rank.
I mean, so this is some very, so this is some very small sort of subset of all elliptic curves. But again, there are x1/2 elliptic curves with a 3 isogeny, whereas there are x to the 5/6 elliptic curves without a 3 isogeny. Okay. So yeah, so I mean, the fact that this sort of grows like log, I mean, it's huge in some sense, but it's tiny compared to sort of that gap between the sizes of these sets. Okay. So I think it's sort of, I mean, you sort of have the put-in-range predictions, of course, sort of for how, say, 3-Selmer ranks should be distributed in the family of all elliptic curves, and I think that sort of those are pretty robust. Yeah. Is there another question? Yeah.
Can you get an absolute bound on the rank for twists? Like you fix an elliptic curve with 3 isogeny. Does that prove you have like some absolute bound on the rank?
No. Are you sort of, at least as I'm interpreting your question, are you sort of asking about boundedness of ranks, sort of like in a family of quadratic twists? No. I mean, yeah, we can't touch that. Okay. Yeah. Well, it indicates a large 3-Selmer rank. Well, again, it's sort of, what this is kind of saying is that, going back to the previous slide, sort of the fact that these averages decay, or these proportions decay, kind of corresponds to the fact that typically you have lots of Selmer elements. You should not actually expect some sort of bounded average, which is kind of what leads to these sort of absolutely bounded proportions you get. Here you sort of know that these things have to decay as your elliptic curves get more complicated. I can also say that sort of this works sort of for elliptic curves over an arbitrary number field. Okay. Again, we give you some recipe to read off things very much like this. Okay. All right.
What if you, even if your curve, if your modular curve didn't have genus 0,
Yep.
I mean, if it's like
an elliptic curve.
or something, right? I mean, you're going to have lots of points over quadratic fields. If you average over, let's say, points on x11 over quadratic fields, like
Yep.
somewhere over that field, you get the same kind of growth.
So it's actually analytically a much harder problem. It sort of connects to some other things, which I'm happy to talk to you about. I think we can get some sort of weak results. Like we can probably prove that the average size of Phi-Selmer is unbounded. But I don't think we'll be able to get something like this, for example. Okay. All right. OK. But again, kind of going back to sort of what we had sort of originally sort of in this talk, we're looking at families of quadratic twists of elliptic curves with a 3 isogeny. We come up with sort of very explicit bounds on the average rank, okay? The number of rank 0 twists and the number of rank 1 twists. Okay? And this also works over number fields. Okay? Okay? And there, it's sort of the story is pretty much exactly the same. I mean, this theorem literally holds with E over a number field K. But it turns out you can get some other kinds of interesting behavior showing up. So for example, it turns out there are examples of elliptic curves for which you get 50% of twists being rank 0. Which sounds great. It sounds like we've proved part of Goldfeld's conjecture. But it actually turns out for these elliptic curves, all of these twists have positive root number. So in fact, you expect 100% of sort of these twists to have rank 0. We can only prove 50%. So this is actually, in fact, the same 25% that we saw before. But OK, I will stop there.
Couple quick questions.
So you mentioned this also works in number fields.
Yep.
So given an elliptic curve defined over Q, it has a 3 isogeny over some extension.
Mm-hmm.
Can you use the results over the extension to conclude anything about the behavior over Q?
No. I mean, that's a great question. And I sort of certainly would love to be able to do that. But the issue is, so basically, if you sort of base change your elliptic curve to some other field, you're now looking at the family of quadratic twists over that entire field. You're looking at all quadratic extensions of that field, for example. And sort of those twists that are coming secretly from Q are a very thin subset. And so if you have ideas on how to attack those things, I have many other applications for that as well. We should talk, but no, I have no idea how to do that right now. So so the answer is basically no. So we're actually sort of in a very good situation. So by the work of the Dock-Chitzers, we sort of know the p-parity conjecture. Okay, and so particularly we understand the root number of these twists. We understand sort of this sort of set Tm. It actually turns out that those parities have to agree. Okay? And so we sort of already know quite a bit about sort of parities of Selmer groups and sort of.
You know what they only have, like, I think they have, like, they divide their family into subfamily where they know the parity conjecture is true. They've already in that situation.
Yes, I mean, we know the parity conjecture is true for every elliptic curve in our family. Or, well, I guess sort of nearly that is true, I guess I should say. The p-parity conjecture is true, so as far as our applications to 3 Selmer ranks, we're happy. Okay. And so that sort of gives us certainly some traction. We exploit that in getting sort of good bounds on these things. Absolutely.
Could you try to run the same game with like quadratic twists with hyperelliptic curves as elliptic Selmer?
I mean, you'd sort of need the analog of this parameterization, and that, I think, would be a little bit uglier. I mean, sort of we're really exploiting the fact that sort of because you have this phi isogeny, you sort of have this sort of, order 3 subgroup. But if you sort of have some analogous scenario for hyperelliptic curves, then maybe, yeah, actually, I'm not sure. That'd be sort of an interesting question. I mean, certainly people do look at sort of the analogs of things like Heath-Brown or Mazur-Rubin for hyperelliptic curves with sort of whatever 2 torsion. And so we sort of understand how those vary in quadratic twist families. So yeah, it'd be sort of natural to look at some sort of analog of this in that case. But I'm not sure offhand what that would be.
Are there families
Sorry.
either defined by like isogeny or like torsion that grow faster than like x to the 1/2 or? Presumably you can't actually get 5/6, but can you get higher than, or can you get 5/6?
I don't think you cannot get 5/6. So I think my answer is I don't know of any. So for example, if you look at elliptic curves with partial 2 torsion, like 1 2 torsion point, which is the same as having a 2 isogeny, that grows like x to the 1/2. Okay. Yeah, I'm not sure of one offhand. Okay. And so I suppose it's actually possible you could sort of write down the various possibilities. It's maybe possible that one doesn't exist.
So I don't know anything about these things, but I understand that the finiteness of SHA is a pretty big open problem.
Mm-hmm.
But is anything known about how often it's finite, or like what proportion? I don't understand. How strong is that condition?
So I think in our setting, very little is known about that. So you can do in the family of all elliptic curves in the same paper of Bhargava, Skinner, and Zhang. So again, they sort of look at the analytic side of things. We sort of know progress toward sort of the analytic side of BSD, sort of implying sort of the arithmetic side. Okay? And you can prove something like a little bit more than 66% of elliptic curves have analytic rank either 0 or 1, and that forces SHA to be finite. Okay? So maybe it's actually possible, thinking about this, that sort of the results of Chris and Lee might say something here about finiteness of SHA as well, but sort of, again, sort of their twists are sort of a subset, sort of of our twists. And so I think sort of as far as getting finiteness of SHA there, no, I don't know how to do that without doing some sort of analytic machinery. Yeah, that's a good question. So I think the way I like to pitch it is this. So if you want to pick a random elliptic curve with a 3 isogeny, okay, you could pick a random elliptic curve and check if it has a 3 isogeny. Okay, that's sort of what happens when you order by naive height. Okay? I kind of think that's a bad thing to do. Okay? I think it's much better to write down the universal elliptic curve and then choose the parameters sort of randomly in some sense. So that's kind of what we're doing here. You sort of have some rational parameterization of your modular curve. We're choosing some sort of random J invariant of bounded height, okay? And then sort of choosing some twist from that, okay? If your sort of modular curve admits twists. Okay. And so I would say that sort of in sort of small degrees, these things should probably be commensurate. Okay? But for large degrees, you can actually get different counts. Okay? You can sort of get completely different behaviors of these things.